So we have this question that a balloon is moving up vertically upward with constant acceleration g upon 2 in the upward direction. Particle A was dropped from the balloon, and 2 seconds later, another particle B was dropped from the same balloon. Assume that the motion of the balloon remains unaffected. Find the separation distance between the particle A and particle B 6 seconds after dropping the particle B. None of the particle reaches ground during the time interval under consideration. Right. So in this question, the balloon is given that's moving upward with the constant acceleration g upon 2. So if it's moving upward with the constant acceleration g upon 2, it means that it's going to maintain a constant increase in the velocity in upward direction. Right? That's how the constant acceleration is going to be constant. So here we will take the upward direction as negative and the downward direction as positive as per our sign conventions. So now we will trace the motion of the particle A and particle B. At first, let's suppose at time t. Let us suppose at time t, particle A was dropped. Particle A was dropped from the balloon. So the time under consideration is t. So at time t, what's going to happen? There will be some velocity, upward velocity of the balloon. Let's keep that u. And when the particle A was dropped from the balloon, it will have the same velocity as that of the balloon. That's going to be u, and it's going to fall under the acceleration due to gravity. That's t. Okay, this is the thing that's going to happen at time equals to t. But what's going to happen in 2 seconds? At time t equals to 2 seconds. In those 2 seconds, the balloon will travel in the upward direction and the particle A is going to fall in the downward direction. So there will be this separation between the balloon and the particle. In those 2 seconds, there's going to be the separation between the two. So how much has the balloon and the particle A separated in 2 seconds? We will first figure out that. Then we will see that at the time t equals to 2 seconds, the particle B was also dropped. Don't forget that. So what's the separation between A and B? We know that the balloon is going upwards and the particle A is going downwards. So they are having the relative motion with respect to each other. We will keep particle A in rest and we will give its velocity and acceleration to the balloon. So it's in the opposite direction. If the velocity of particle A is in the u in the upward direction, once given to the balloon, the velocity is going to come in the downward direction, and the acceleration of particle A is in the downward direction. So the acceleration of balloon is going to come in the upward direction g. Okay, so acceleration of balloon with respect to particle A comes out to be g plus g upon 2, and that's going to be 3g by 2. And velocity of balloon with respect to particle A comes out to be u minus u, and that's going to be 0. So the separation, we will use the second equation of motion. Separation of balloon with respect to particle A in 2 seconds is going to be, first term is going to be 0. Half of, what's the acceleration? 3g upon 2 multiplied by the time under consideration is 2 seconds. So it will be 2 squared. This 2 squared and the bottom 4 is going to get cancelled. So the separation of balloon with respect to particle A in 2 seconds comes out to be 3g. Right? So let's take the next slide. So we will say that I will say that in 2 seconds the particle A and the balloon has separated by a distance equal to 3g. So we will say that in 2 seconds the particle B has reached somewhere here. Particle A, this particle A, and the distance between the two, separation distance, is 3g when the time was 2 seconds. At this time the particle B was dropped. At this time the particle B was dropped from the balloon. The particle B was dropped from the balloon at time t equals to 2 seconds. So in those 2 seconds the velocity of A has changed, the velocity of balloon has changed as well. So first we need to figure out what's the velocity of balloon at time t equals to 2 seconds. It's going to be upward. Let's keep that VB. We need to find out what's going to be VB in time t equals to 2 seconds. So VB is going to be, its initial velocity was u in the upward direction. Since the upward direction is negative, I will take it minus u, plus its acceleration was upward direction g by 2, so it will be negative, multiplied by t equals to 2. So the velocity of balloon after time equals to 2 seconds is going to be minus u minus g. And what's going to be the velocity of particle A at time t equals to 2 seconds? It's going to be downwards. VA is going to come out to be, what's its initial velocity? It's minus u, plus its acceleration is downwards, and 2g. This is going to be the velocity of A at t equals to 2 seconds. So at time t equals 2 seconds, the velocity of balloon is minus u minus g. And at the same time, we are dropping the particle B. So the particle B is going to have the same velocity as that of the velocity of the balloon at time t equals to 2 seconds. So velocity of the particle B is going to be minus u minus g. Now, already the particle A and particle B are separated by the distance 3g at time t equals to 2 seconds. Now, what's going to be the further separation for time for 6 seconds? How much they are going to separate now for 6 seconds? Again, they are in the relative motion. So what we are going to do, we are going to keep the particle B in rest, and we are going to give its velocity and acceleration to the particle A in the opposite direction. So now, keeping particle B at rest, we will take velocity of particle A with respect to particle B is going to come out to be, what's the velocity of particle A? It's minus u plus 2g, and it will be subtracted by the velocity of particle B since it's in the upward direction, minus u minus g. So the velocity of particle A with respect to particle B comes out to be minus u plus 2g plus u plus g. Minus u and plus u gets cancelled out. So the velocity of particle A, relative velocity of particle A with respect to particle B comes out to be 3g. And what's the relative acceleration? Relative acceleration of particle A with respect to particle B comes out to be 0. G in the upward direction and g in the downward direction. So the total is going to get cancelled out. Now we will use the formula. Separation of particle A with respect to particle B in those 6 seconds comes out to be UAB multiplied by T, and the second part of the equation is going to come out to be 0 because the acceleration is 0. So the separation of particle A with respect to particle B is going to be given by UAB is given by 3g, and we are tracing the separation in 6 seconds. So the separation of particle A with respect to particle B comes out to be 18 times g. What's the total separation? Total separation. Total separation. You need to focus on one thing. Particle A was dropped, okay, and in time t equals to 2 seconds, the separation of balloon with respect to particle A was 3g. After time t equals to 2 seconds, particle B was dropped. And in those 6 seconds, the particle A and particle B that were already separated by 3g distance are separated by the distance equals to 18g. So what comes out to be the total separation? Total separation will be equal to 18g plus the initial separation that was 3g, that's coming out to be 21g. So g equals to 10 meter per second square, that's 21 into g, which is equal to 21 into 10 meter per second square, or it's going to be 210 meters. Thank you. Hi. So the question that's given here is that how the level of water changes when an object is initially floating and then sunk. Let's explain the question first. The question asks us that if we take a situation like this, that there's an iron block kept on the ship that's floating on the water. So if somebody comes and throws this iron block inside the water, what's going to happen with the levels of the water? Are the levels going to rise? Is the level of water going to decrease, or is the level of water going to remain the same? This is the question. So let's tackle this question. We are going to use two concepts over here. two very important and very easy concepts from flotation. One is that the first one being that we call that as law of flotation. Law of flotation. And what is the law of flotation? Actually, law of flotation says that when can you say that an object is going to float on the surface of water? So when is that going to happen? You know that whenever we keep an object on the surface of water, then that object can float or that can sink. It can sink in the bottom of the river or the water based on the densities of that object, how high or how low the density of that object is. But in case it's going to float, still some part of the object is going to be immersed inside the liquid, as you can see over here. The ship is floating on the water, but at the same time, some part of this ship that I'm coloring right now, it is immersed in the water. Okay, so when this part of the ship will be immersed in the water, what's going to happen? This part is going to displace the water, right? It's going to take the place of water. It's going to displace the liquid from its place where from it's immersed. And how much liquid is it going to disperse? It's going to disperse the liquid that's equal to the volume of this immersed part. Okay, so number first thing, volume of volume of liquid displaced volume of liquid displaced is always going to be equal to the volume of the immersed part. Volume of the immersed part. So it means that that part of the object that's immersed in the liquid is going to displace the water equal to its volume. Okay, now what's law of flotation? Law of flotation says that when this ship is inside the water and some part of it's immersed in the water, we can say that it has displaced some amount of water. Let's take that here. So this is the amount of water that's displaced by the ship. Okay, when it has displaced some amount of water, now what's going to happen? Law of flotation says that if the object floats, the weight of this liquid displaced, the weight of liquid displaced is going to be equal to the weight of the is going to be equal to the weight of the object. Very important. So what's happening here? The weight of the liquid displaced is being balanced. The weight of the object is being balanced by the buoyant force that you will study in the Archimedes principle. I will skip that here. So this is the law of flotation that we have. These two concepts. Number first, that the volume of the liquid displaced is equal to the volume of the immersed part. Number second, weight of the liquid displaced is equal to the weight of the object. These two concepts we will use to solve this question that's given to us. Now at beginning, let the mass of this iron block or iron cube be small m. And mass of the total system. What's the total system? The total system consists of the iron block and the ship. Mass of the system, let me denote that mass of the system by capital M. Okay, now let's move forward. I can use the formula that weight of the liquid. What's going to be the weight? Weight is mass into acceleration due to gravity. So what's the mass of this total system? It will be m, capital M, multiplied by g, is going to be equal to weight of the liquid. This is the weight of the object. It's going to be equal to the weight of the liquid displaced. So what is the weight of the liquid displaced? Since I don't know its weight, so I will take help of this formula that density equals to mass per unit volume, or from here I can get that mass equals to density times volume. Okay, so I will express the mass of the liquid displaced as density of water times the volume of liquid displaced. This will be the mass multiplied by g. That's how I will work this equation. This g and this g gets cancelled out, so I am left with that the volume of liquid displaced in the first case when the iron block was on the ship, it's equal to the mass of the system upon the density of water. Let's keep this equation here as equation number first. Now we will focus on the second situation. Now what's happening here? Somebody came, let's suppose, I'm really sorry. Okay, let us suppose somebody came and threw this iron block inside the river. Okay, once this iron block is thrown inside the river, we can watch it all the way until it reaches the bottom of the river, right? Now what's going to happen in this case? What's going to happen with the volume of the liquid displaced? And that's how the levels of the water are going to change. So here in this part, we are going to use the formula that volume of liquid displaced is equal to the volume of object, volume of objects, or volume of the immersed part of the object in case it's floating. So now in this case, volume of liquid displaced, volume of liquid displaced, let's keep that V2 equals to, now what's the volume displaced, volume of the liquid displaced by the cube? We will take it like the same formula, density equals to mass per unit volume, and volume will be equal to mass per unit density. So I kept the mass of the iron block as small m upon its density will be rho of cube, or rho of iron I will take here, density of iron, plus now what's happening here, once that iron block was dropped off the ship, the weight of the ship or the mass of the ship is going to get reduced. There's going to be the decrease in the mass of the ship, and if there is going to be the decrease in the mass of the ship, the weight of the ship is also going to decrease, and if the weight of the ship is going to decrease, the volume of the water displaced is also going to be decreased, right? So now what's the mass of the ship? If m was the mass of the system, we will take away the mass of the iron block, that will give me the mass of the ship, upon, we know that the volume of the immersed part of the ship, okay, it will be equal to the volume of the water displaced. We can take density of water here, since it's floating, we can take easily the density of water. So second time the volume comes out to be mass of the system upon density of water, plus mass of iron cube upon density of iron cube, minus mass of iron cube upon density of water. Okay, this is V2. Let me write V1 here. V1 was the volume in the first case, you can see clearly, volume of the liquid displaced in the first case was mass of system upon density of water. At that time the liquid was water. Now if I have this thing equal to V1, I can replace it here. So I can write V2 equals to V1 plus mass of iron cube upon density of iron minus mass of iron cube upon density of water. Now this term is going to define whether the volume in the second time is going to increase or decrease. Now we know that density of iron is very greater than density of water. So if the density of iron is more, this complete term will become small. It's going to be small. And if the density of water is less, this complete term is going to be larger than the other one, because the numerators are same, only the denominators are changing the values. So if this is going to be the large, we are taking away the larger term from the smaller term, so the complete result of this thing is going to be negative. And if it's negative, we will get an answer that V2 is going to be more than V1. Sorry, we will get that V2 is going to get reduced than V1, so it's going to be less than V1. So what does that mean? If the volume of the water displaced in the second case is less, what's going to happen to the level of water? So the levels of liquid are going to decrease, Thank you. Hi. So the question that's given to us is that we are given a biconvex lens whose focal length is 20 centimeters. It's placed 5 centimeters in front of a convex mirror whose focal length is given to be 15 centimeters. An object of length 2 centimeters is placed at a distance of 10 centimeters from the lens. We have to find the location of three images. Number is that the image formed by the lens as the rays travel to the right. Number second, the image formed after the rays reflect from the mirror, and the final image after the leftward traveling rays once again pass through the lens. Let's take this question. Here we are given a biconvex lens. We are given a biconvex lens that's been placed in front of a convex mirror. It's being placed in front of a convex mirror. And it's being placed at a distance of 5 centimeters from the convex mirror. That's given in the question. Apart from that, the focal length of the convex lens as well as the convex mirror is given. The object distance is given in the first case. We have to determine the image distance in all the three cases. Okay, so we will begin with this. The first thing that you need to know here is what formulas and what concepts that are we going to use in this question. The first thing is that we are going to use the sign conventions. For the convex mirror, all the distances measured from the pole and the distances in the direction of incident ray are taken as positive. So for the convex mirror, that will be the sign convention. We will measure all the distances from the pole, and the distances from the pole which are measured in the direction of incident light are taken as positive, and which are measured opposite to the direction of incident light are taken to be negative. Now the second thing is that all the distance is measured from the optic center of the biconvex lens. For the biconvex lens, the reference point will be the optic center to measure all the distances, and every distance that's taken in the direction of incident ray from the optic center is going to be positive, or else it's going to be negative. We will be using the mirror formula and the lens formula, the formulas that relate the image distance, object distance, and focal length in both of these mirrors as well as lenses. So let's take the first part. The first part says that when an object is placed at 10 centimeter, let's say this is the object, it's placed at 10 centimeters from the lens, and this is the optic center of lens. If we want to measure the object distance in this case, we have to start from the optic center and directly reach to the object, right? This is going to be the object distance, which is given as 10 centimeters. But whether it's positive and negative, we will decide from here. We know that if this is the object, the incident light is going to pass in this direction. This will be the direction of incident ray. This will be the direction of incident ray. And in order to measure the distance, how far the object is placed from the lens, we have to start from the optic center and move towards the left. So now we are going opposite to the direction of incident ray. So the object distance in this case comes out to be negative. It's minus 10 centimeters. Number first thing. The focal length of the biconvex lens is positive. F1, it's given out to be how much? 20 centimeters. F1 is given as 20 centimeters. We have to determine that in this case where will be the image located. We will use the lens formula. What's the lens formula? 1 upon V minus 1 upon U equals to 1 upon F. 1 upon V minus 1 upon U equals to 1 upon F. Now, as per the lens formula, 1 upon V minus, what's the object distance? It's minus 10 centimeters. It's going to be equal to 1 upon F. What's the focal length? It's 20 centimeters. 1 upon V, it will be negative, and to negative will be positive, and when taken on the other side, it will again become negative. 1 upon 20 minus 1 upon 10. Now 1 upon V comes out to be 10 minus 20 upon 200, and upon doing the cancellation, we will get 1 upon V equals to minus 1 upon 20, or we can write that V equals to minus 20 centimeters. This is the first case. So we have located the image in the first case. In the first case, V comes out to be minus 20 centimeters. Minus 20, here the negative sign suggests that from the optic center of the lens, we have to travel in the direction that's opposite to the incident ray. So from the optic center to the place where the object was kept, we have 10 centimeters. So it means from the object we have to travel 10 centimeters more to the left, and in total the distance from the optic center to the image is going to be 20 centimeters, and this is where the image is going to be located in the first case. First case. Now this image, very important here, I will erase this part now. Now this image is going to act as an object for the mirror. It's going to act as an object for the convex mirror. And if it's going to act as an object for the convex mirror, and we need to see where will its image form, where is it going to reflect, inside or outside the convex mirror, we need to know the object distance. So how will we find object distance? We know that this image is formed at a distance of 20 centimeters from the lens, and the lens is kept at a distance of 5 centimeters from the mirror. So the total object distance is going to be 20 plus 5, that's going to be 25 centimeters. So in case of the mirror, in case of the mirror, we know that the object distance is going to be 25 centimeters. But what about the sign conventions? From the pole of the mirror, in order to locate the object, we have to travel in this direction, but the light, incident light, is going to travel in this direction, so we are going in the opposite direction, so it's going to be negative. But at the same time, the focal length of the convex mirror, how much is it given? It's given as 15 centimeters, and the focal length of convex mirror is going to be positive 15 centimeters, because we will travel in the direction of incident ray. And we have to find the image distance in this case. Now which formula we are going to use? We are going to use the mirror formula, because we are dealing right now with the mirror. So 1 upon v plus 1 upon u is going to be equal to 1 upon f, which implies 1 upon v plus 1 upon u is minus 25 centimeters is equal to 1 upon f. F is given to be 15 centimeters, which implies that 1 upon v is going to be equal to 1 upon 15 plus 1 upon 25. While taking the LCM, 75 comes out to be the LCM of the both of the two. 15 into 4 is 60, 15 into 5, and 25 into 3. So which implies 1 upon v equals to 8 upon 75, or I can write that v equals to 75 upon 8 centimeters. So we know that 8 9s are 72, so it's approximately 9 centimeters. Approximately 9 centimeters. We will keep it 75 upon 8. But to know one thing here, that the image distance here comes out to be positive. So as per the sign conventions, from the pole of the convex mirror, in order to go in the positive direction, we have to travel in the direction of incident light. So this is the direction of incident light, so we will travel towards this side. So this is going to be the image. This is going to be the image in the second case. Okay, how far? It's going to be 75 upon 8 centimeters from the pole of the mirror. Now this image is going to act as an object for the lens again. It's going to act as an object for the lens, and now we have to see how, where this lens is going to reflect it or refract it. Now this image is here in the second case, that will now act as an object for the convex lens. Biconvex lens, it is 75 upon 8 centimeters, and from the biconvex lens the mirror is placed at a distance of 5 centimeters. Now there will be a different image distance. What's the object distance in this case? Object distance is going to be 5 plus 75 upon 8, right? And is it going to be positive or negative? You know that right now, very important to focus here, right now, if the object is placed here, this will be the direction of incident light. This will be the direction of incident ray. And this is the optic center. We have to locate the object, so we are traveling opposite to the direction of incident light. So again, the object distance here is going to be negative. So what's the object distance here? It's going to be 40 plus 75 upon 8, and all of this is going to be negative. It's going to be 105 upon 8 negative centimeters. Okay, now the focal length is given. How much is the focal length of the biconvex lens? The focal length of the biconvex lens is given as 20 centimeters. So the focal length is 20 centimeters, and we have to locate the image in this case. So we will use the lens formula, 1 upon v minus 1 upon u equals to 1 upon f. So as per the lens formula, 1 upon u equals to 1 upon f, which implies 1 upon v equals to 1 upon f plus 1 upon u, or I can insert the values 1 upon v equals to 1 upon, how much is the focal length here? Focal length is 20 centimeters. And this negative will come with a sign. So minus 1 upon, I will take the positive value of u now. It's 105 upon 8. So I can write this thing as 1 upon v equals to 1 upon 20 minus 8 upon 105, which implies to me 105 minus 160 upon 20 multiplied by 105, which comes out to be 1 upon v will be equal to 105 minus 60 is 55, but it will be negative, minus 20 into 105, 105 into 20, 105 into 0 is 105, and 105 twice is 210, 2100. Or I will write that v equals to 2100 upon 55, and the sign is going to be negative. Now we know that it's going to be somewhere approximately equal to 50 centimeters, but it's going to be negative, right? What's the direction of the instant light that we took here? This was the direction of the instant light. So we are tracing the image formation as per the lens. This is the optic center, and we have to travel in the negative direction. What's the negative direction? It's going to be this direction. That's going to be the opposite. So from here to here, it's 5 centimeter. From the pole of the mirror, it's approximately 45 centimeters. So this is the image, and we will say this is the final image formed. This is where the final image will be located, or I can write it, it's at a distance of 2100 upon 55 centimeters from the lens. Okay, thank you.